Welcome back to Unit 3. More on solutions. This lecture is on solubility and the concentration of a solution, and it's page 184 to 188 in your textbook. By the end of this lecture, you will be able to relate the solubility of a substance in water to temperature and pressure. You'll be able to describe the concentration of a solution based on the amount of solute in a solution. You'll be able to perform calculations involving concentration, and you'll be able to express concentration as percent by mass and parts per million. So first, for solubility, some definitions. The first one is saturated solution. A saturated solution is a solution with the maximum concentration of a solute at a specific temperature and pressure. If any more solute is added, then it will not dissolve. The solubility of a substance, or the amount of substance that can be dissolved in a liquid, and in this case we're talking about water, is affected by both temperature and pressure. For solids, solids are more soluble when water is at higher temperatures. And for this, you can think about your coffee. As coffee cools, if you add sugar to your coffee, you'll find that sugar comes out of solution. And at the bottom of your coffee, if you let it sit, so you add 4 or 5 sugars to your coffee, if you let it sit and cool off, you'll find that the amount of sugar that builds up in the bottom of the cup increases as the coffee cools. Gases are actually the opposite. They have higher solubility in water at low temperatures. So cold water can hold more gas than warm water. And if you think about, if you fill up a glass with cold water, say from your fridge, if you leave it out on the counter, what you'll find is as it warms, you'll get bubbles inside the glass, and those bubbles are the gases coming out of solution as the water warms up. Gases have higher solubility in water at high pressures, so as you increase the pressure of a gas, if you're able to compress that gas, you can actually force it into solution. In terms of talking about liquids, liquids are either going to be immiscible, so they're either not going to mix with water at all, such as oil and water, they sit in separate levels, or they're completely miscible, which means there's actually no saturation point. You can always add liquids such as alcohol and water can be mixed in any proportions, and you get an evenly mixed solution, or a solution that has the same properties throughout, regardless of the amount of alcohol or water present in the solution. Generally speaking, with elements in their pure form, elements have low solubility, with the exception being halogens, those group 17 gases, and oxygen. They are slightly soluble in water. In terms of defining concentration, concentration is defined as the ratio of the quantity of solute to the quantity of solution. So we're measuring the amount of solute, and we're measuring the total amount of solution that we have, and comparing the two. A dilute solution is one that would have a relatively small amount of solute per unit volume, whereas a concentrated solution would have a relatively large amount of solute in solution. Mathematically, this can be expressed as all of our concentration formulas are going to be versions of this basic formula, where we take the quantity of the solute, which is either going to be measured in grams or moles, depending on the situation. So grams or moles. And the quantity of our solution, which is either going to be in grams or liters, depending on how we're calculating concentration. So there are 3 main ways to calculate concentration. One is percent by mass, and this is usually done when we're dissolving solids into a liquid. This is especially used in commercial products. parts per million. For very dilute solutions, ones where the concentration of our solute is very, very small, but still needs to be known. It's often used for air quality conditions, so the measure of particulates in air or other gases as they relate to the total volume of air. And finally, by molar concentration or molarity. Now this is going to be the most used form of calculating concentration in chemistry, in our chemistry class. So we'll start by talking about mass by percent. It's used for solid solutions. So for alloys, you'll see concentration is mass by percent. For high concentration of compounds in water, salts and waters, and also in commercial products. In terms of the formula, so it's still going to be the quantity of solute is going to be measured as mass in grams, and this is important that you get the units right. It's going to be grams of solute over grams of solution. Remember, solution is actually the mass of solute plus the mass of solvent. So now we're going to work through some examples. First example, we'll look at a sample of road slush from winter, which is never fun to think about, but here we go. It weighing 23.47 grams. When all the water is evaporated, 4.58 grams of calcium chloride in the residue remain. We're going to calculate the percent mass of calcium chloride in the road slush. So the first thing we'll do is we'll write down our formula, and percent mass is equal to the mass of solute divided by the mass of the solution times 100%. We have two masses here. The 4.58 grams would be our mass of solute, and the 23.47 grams would be our mass of solvent. Or not solvent, sorry, this is a mass, and this is where we got to be really careful in choosing the right terminology. This is the mass of our solution. It's the total mass of the road slush, which includes the mass of the calcium chloride. So that's the mass of our solution. So we have everything we need to calculate our percent mass. It'll be 4.58 grams divided by 23.47 grams times 100%. When we run that through our calculator, we get an answer of 19.5%, and this is rounded to 3 significant digits. And there we have it. And for units, we should put those in. It's 19.5%, and then we put mass by mass. You can measure concentration in terms of volume by volume, or mass by volume. So we're doing mass by mass. It's the mass of the solvent divided by the mass of the solution, so that little m over m lets people know what quantities we're comparing. Here we have a sample of whale water, for example 2, containing 0.24% mass by mass of dissolved iron. And we're going to figure out the mass of iron present in 1.2 liters of this water. And now, when we take a look at this statement here, 1.2 liters of this water, since it's talking about the water with the iron in it, this is going to give us the mass of our solution. It includes the mass of the iron, because the iron is already dissolved in this water. And because we're working with water, we know that the density of water is equal to 1 gram per milliliter. So once we figure out how many milliliters we have, so since we have 1.2 liters, this is the same as 1200 milliliters, which means we have 1200 grams of H2O of solution. And so it's important to make sure you get those units converted from liters to grams. And so percent mass is equal to the mass of the solvent, or solute, sorry. Words always come out at the wrong time. mass of solution times 100%. Now we have our percent mass, and so this is where you're given a little bit of choice. I'm going to use some formula manipulation first to isolate the thing I'm looking for, and then I'm going to plug my numbers in. So I'm going to divide both sides by 100, because I want to isolate my mass of solution, so divide by 100%. And then I'm going to multiply both sides, and what that does is, on the right side it cancels. I'm going to multiply both sides by the mass of my solution. So mass of solution on this side, multiply by mass of solution on this side. And what that does is it isolates our mass of solute. So the mass of solute will be equal to percent mass times the mass of our solution over 100%. And now we can plug in our numbers. So we have 0.24 times the mass of our solution is 1200 grams divided by 100, and if we just put our percents in there, you can see the percents cancel out, and we'll be left with an answer in grams. And once you run everything through, 2.88 grams. And this is the mass of iron in 1.2 liters of well water from this particular well. Another example, we have a solution of hydrochloric acid is prepared by bubbling 27 grams of acid into 150 ml of water. We want the percent concentration. So, write down our formula here. Percent concentration, or percent mass, is equal to mass of solute over the mass of solution times 100%. And here we have to be a little bit more careful. We have 27 grams of acid, 150 milliliters of water. This means the mass of solution is equal to the mass of your solute plus the mass of your solvent. So we actually have to add these two masses together to get our mass of solution before we can calculate percent mass. So we're going to end up with 27.0 grams over 27.0 grams plus 150 grams, because 1 milliliter of water weighs 1 gram, times 100%, which would be 27.0 grams over 177 grams times 100%. And when you run it through your calculator, we should end up with 15.3% mass by mass. So the hardest, I think, or the most difficult part with these questions is making sure you know what your quantities actually are when they're given to you in a question. So here we have a saline solution administered intravenously to restore electrolytes in people suffering from traumatic injury. We're going to determine the mass of water required to prepare a 0.95% solution using 1.54 grams of sodium chloride. So here we're looking for a mass of water, or what we're really looking for, it's not the mass of the solution, but actually the mass of our solvent. So in terms of our formula, we're going to break it up a little bit, and we're going to say percent mass is equal to the mass of the solute divided by mass of solute plus the mass of solvent, put that in brackets, times 100%. So the mass of the solute, and here we're going to do a little bit of algebra ahead of time. We want to isolate the mass of the solvent. So in order to do that, I'm going to multiply both sides by the mass of solvent plus mass of solute. When we do that, we end up canceling it out on this side, and we end up with, I'll just clean this up a little bit. So mass of solvent plus mass of solute times our percent mass is equal to the mass of solute times 100%. Divide both sides by percent mass. And finally, we're going to subtract the mass of our solvent. So the algebra is a little bit more complicated, but the mass of our solvent is equal to the mass of solute times 100 over our percent mass minus the mass of our solute. And that will give us the mass of water we need to make this 0.95% solution. So the mass of our solute is 1.54 grams times 100% divided by 0.95% minus 1.54 grams. When we run the first part of our equation through, we end up with 162.1 grams minus 1.54 grams, and we end up with 161 grams once we round it off to 3 significant digits. So the mass of water needed to make this solution would be 161 grams. When we add 161 grams of water to our 1.54 grams of sodium chloride, we end up with a solution with a concentration of sodium chloride of 0.95%. So the other way we can calculate concentration is by parts per million. It's used for very dilute solutions, concentration of carbon monoxide in air, concentration of hydrogen sulfide in air. It's also used if you take a look at your bottled water, when they show you the dissolved minerals, they're usually in parts per million or parts per billion. And so for parts per million, it's equal to the mass of the solute divided by the mass of the solution. You'll end up getting a really small number. And so to get your parts per million, you're just going to multiply your answer by 10 to the 6th. And what this does is it tells you how many grams of solute are in a million grams of solution, or a million parts of solution. So it's actually counting gram per million grams. If you want parts per billion, which a lot of times you'll find on water bottles, it's the same thing. It's going to be the mass of solute in grams divided by the mass of your solution in grams. The only difference is you're going to multiply it by 10 to the 9th, and that's going to give you your parts per billion. So here we have cigarette smoke. The average smoker inhales 18.3 milligrams of carbon monoxide from one cigarette. Calculate the concentration of carbon monoxide in the body of a smoker with a weight of 60 kilograms. So when we're doing these questions, the first thing we want to do is make sure we get our numbers in the right units. It's 18.3 milligrams. This is going to be the mass of solute. 60 kilograms. Since this is the whole person, this is including the weight of the carbon monoxide, so this is actually going to be the mass of solution. Even if you added that 18.3 milligrams to your 60 kilograms, in terms of sig digs, it doesn't make a difference. 60 kilograms is 60,000 grams. 18.3 milligrams is 0.0183 grams. So they differ by a factor of almost a million. So adding the two together to get the mass of your solution isn't necessary because they're at such different magnitudes in terms of the size of the number. So we want our parts per million. So concentration in parts per million is going to be mass of solute over mass of solution times 10 to the 6th, and this is going to give us our parts per million. The mass of the solute, make sure we write it down in grams, so 0.0183 grams divided by 60,000 grams times 10 to the 6th. Run it through and we end up with 0.305 parts per million. And I guess because we only have two sig digs for the weight of our person, it's going to be 0.31 parts per million. This is about 100 times less than toxic levels that will kill you right away. You have to multiply that by about 100 before you have to worry about it killing you immediately, but it's still enough to kill you in about 40 or 50 years if you do it every day at a pack a day. But that's enough of my diatribe against smoking. Alright, so here we have drinking water with fluoride to help prevent tooth decay. The concentration of fluoride in city waters is, and here they give us the concentration, 0.93 parts per million. And we're saying the average person consumes about 1.5 liters of this solution every day. So this is our solution, and this is our solute. So the first thing we're going to do is calculate the mass of fluoride consumed, and then we're going to recalculate our concentration in one person. So this is the percentage, or I should say the parts per million concentration in the water. This will be the parts per million concentration in a single person, assuming they don't lose any of the fluoride throughout the day. So first we'll calculate the mass of fluoride consumed. So here we have concentration in parts per million is equal to mass of solute over mass of solution times 10 to the 6th. And here we know the concentration and the mass of our solution. So I'm going to isolate the mass of solute, multiply both sides by the mass of the solution. I'm going to get concentration in parts per million times the mass of the solution, divide both sides by 10 to the 6th to move our 10 to the 6th over. And so the mass of our solute can be found by taking our concentration, multiplying it by the mass of solution, and dividing by 10 to the 6th. This is actually, let's just shorten up our formulas. In this case, it's the mass of fluoride ions is equal to our concentration in parts per million is 0.93 parts per million. The mass of our solution is 1.5 liters is 1,500 grams divided by 10 to the power of 6, and the units for this would be parts per million. It's nice to write them down just so we can see our units cancel. With an answer in grams, and once we run it through, we should get 0.0001395 grams. We're going to convert that to milligrams, so multiply by 1,000, which is going to move our decimal 3 spots over. 1.4 milligrams of fluoride in 1.5 liters of H2O. And for the second part of this question, I'm just going to erase our work. And so we know that in 1.5 liters of water, we have 1.4 milligrams of fluoride. So if you drink 1.5 liters of water, we're going to calculate now the concentration of fluoride ions in one person, assuming that none of the fluoride is lost throughout the day. So assuming it doesn't come out in your pee. And so here we have concentration in parts per million is equal to mass of, and I'm just going to write like this, mass of fluoride divided by mass of solution times 10 to the 6th. The mass of our fluoride is 0.00014 grams divided by mass of our solution would be the mass of a person, 60,000 grams times 10 to the 6th parts per million. And this is going to be equal to our concentration in parts per million. Once we run the numbers through, we get 0.00233, and this is parts per million. Now, because it's still so small, we can convert this to parts per billion if we multiply by 1,000. And I guess the conversion would be there are 1,000 parts per million in one. Sorry, other way around here. 1 part per billion sorry, I had it the right way the first time. Hold on a second here. I'm just going to erase these scribbles here. I'll try this one more time. So to convert this to parts per billion, there are 1,000 parts per billion in every part per million. So when we multiply this by 1,000, parts per million cancel, we end up with 2.3 parts per billion. That's a concentration of fluoride ions, assuming none are lost in one person's body when they drink 1.5 liters of water. And there we go. There's problems on 186 and 188.